Okay. So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Travis Orloff, who's come up to us from Pierce College in Southern California. Travis did his bachelor's at University of Washington in Seattle, and then came down to the Bay Area to do a PhD at University of Santa Cruz, where he worked with Eric Asfog and Noah Finnegan and Mikhail Kreslovsky on his PhD, which focused on the topic of his talk today, which was boulder clustering and geomorphology of Martian northern latitudes. His career interests have revolved around polar processes, polar geomechanical processes. He has a paper on glacial moraines in Tibet and Antarctic dry valleys. And also papers on Mars, boulder clustering mechanisms, impact structures and statistics of boulders, and on techniques, objectively characterizing patterned ground on Mars. So please join me in welcoming Travis.
Good afternoon, everyone. I'm Travis Orloff, and today I will be discussing boulder clustering on Martian pattern ground terrain. Before I get started, I'd like to thank my funding source, NASA, of course, and SETI for inviting me here today, and then also my PhD institute where I was able to get this research accomplished, the University of California, Santa Cruz, and my co-authors there, Eric Asfog and Misha Kreslovsky, and then also my current institution, Pierce College, as well. So I'd like to jump right into pattern ground on Mars. This is a picture of an impact crater structure that has been heavily inundated by pattern ground terrains. And here what we see is the frost filling the cracks that outline the polygons. And then we also see many, many boulders, like this group of them here. Each one of these shadowed light subjects is a boulder. And these boulders, we assume, were created, or at least are associated with the impact crater themselves. We can use this relationship to tell us something about the timing and mechanism for boulder clustering. So what I hope to do is answer some fundamental geological and climatological questions about the formation and mechanisms for pattern ground. It also gives us a chance to look at the water cycle on another planet and how that involves the surface of the planet itself. I think this is critical for continued robotic and human exploration of the solar system, and we've already sent landers to these very terrains. So we can get a large return on our investment by really studying these terrains. And then finally, since this is a site of water, which may or may not be liquid today, on Mars there's some potential astrobiological consequences for that as well. So to outline my talk, I'm first going to begin with an outline and some background about pattern ground both here on Earth and on Mars. And then I will go into either frost heave or thermal contraction. This picture on the left demonstrates an idea of what a frost heave type polygon might form. In it, we develop convective cycles due to repetitive ice lensing and ice lens formation that will separate, I lost the mic, the fine particles from the more dense, larger particles. Thermal contraction, on the other hand, involves having a very cemented, frozen subsurface that undergoes repetitive seasonal fluctuations in temperature. These fluctuations in temperature cause the ground itself to swell and shrink, which generates cracks when the stresses aren't enough to support or the strength is not enough to support the stresses involved. So here's an example of pattern ground polygons on Earth of the frost heave variety. This is a picture from Ingolfson, 1998. And here you really get to see how integral the water, in this case, is to the formation of the polygons. You have complete saturation of the near surface, and repetitively freezing this surface allows to separate this finer domain, which I'm showing here, and the more gravelly terrain next to it. We also have polygons that can cluster much, much larger boulders as well, or cobbles to boulders in size. Here we show some thermal contraction polygons. You can see the cracks and the furrows. Here, this one's not filled by boulders. But these boulders are about 30 centimeters in scale and completely outline these large polygonal blocks. Here's a picture from the dry valleys of Antarctica that also shows some additional thermal contraction crack polygons. Here you can really see how the ice fills those polygons and forms a wedge that prevents them from closing. That wedge then continues to grow in size, and the polygons continue to grow with them, or subdivide further due to their continued expansion. Now on Mars, we started with patterns of a different type. Schiaparelli in 1886 saw many, many linear features on the surface of Mars, which he assumed were canali. We now have much, much better imagery, though, and we can see new patterns emerge from the surface itself. Specifically, the missions that I will use to discuss our topic today is some results from Mars Pathfinder in 1996, which allowed us to have, and Mars Odyssey as well, which gave gamma ray spectrometry and neutron ray spectrometry data to determine the hydrogen, water equivalent hydrogen in the near surface. Then I will also look at the Mars Reconnaissance Orbiter, specifically HiRISE images, and finally Phoenix, which actually landed on these terrains themselves. And let's see what Phoenix found first. Getting ahead of myself. So the water cycle on Mars can be divided into a few different arenas. We know for a fact there's large water reservoirs in the polar caps themselves. There's some trace amounts of water vapor in the atmosphere as well. And there's water within the regolith too. In the polar caps, there is yearly transfer of this water as water vapor to and from the atmosphere, where it either condenses or sublimes. The water vapor is dependent on seasonal variations and latitudinal variations as well. And we don't really know too much about what is occurring in the regolith, especially deep within the regolith. However, we do have a pretty firm grasp on the uppermost meter of the surface. In that uppermost meter of the surface, there is a lot of water in ice form at high latitudes. This is the results of gamma ray spectrometry that show the water equivalent hydrogen abundance. And what we see is that poleward of 60 degrees, we have anywhere from 25 to 90% water ice in the uppermost meter of the surface by volume. That's a lot of water ice. And we can only penetrate 1 meter down. So there could be much, much more water ice available as well. Now this water ice is going to experience many, many seasonal fluctuations. Carbon dioxide frost freezes out onto the surface seasonally. The temperatures can range anywhere from 150 degrees Kelvin to above 200 degrees, 220 degrees Kelvin, very easily from season to season. And daily temperatures might even exceed the melting temperature of ice itself. So we have lots of ice present, And we know that the seasonal fluctuations in this ice can generate polygonal pattern ground. And so to further explore this terrain, we sent the Phoenix lander. In 2007, it landed. And here we can see an image showing the Phoenix lander in its descent. The HiRISE camera was able to capture it as it fell. Here's Heimdall crater in the background. It's about 15 kilometers away from the landing site of Phoenix. And here in this subset, you can actually see the parachute and the lander itself as it falls from the sky. When we see it from the HiRISE camera on the surface, we can see a number of things as well. First, the terrain itself clearly has this labyrinthine pattern, this texture that covers the entire surface. And then we also can see the parachute, the heat shield, and this here is the lander itself. One of the first things that was done then was to look underneath the lander, and blown away by the thrusters, which you can see at the top of the picture here, these thrusters here blew away the dirt underneath and exposed this white layer, which was definitely thought to be ice. And further experiments showed that it was indeed ice. Here is one of those experiments where we dug into the surface with the Phoenix lander. It has an arm and a shovel that could remove material from the substrate and soils. And what it uncovered was here on Sol 20, we chipped away at this white material and formed a number of white chips, which are down here in this larger image. But then several days later, those chips disappeared. And so those had to have been sublimated away, and that is exactly what we expect from ice. And so we do have ice within centimeters of the surface, and not just any ice. It's not pore ice specifically. It's actually massive ice as well. These are large ice crystals. This here is not ice between sand grains. This is a huge chunk of ice, just centimeters underneath the surface. And another thing that was noticed is that some of the boulders nearby happen to cluster as well. Here we have kind of a mound of boulders, right? And then just a few feet away, there's nothing. And this was something that I began to see over and over and over again. So let's look a little bit more specifically more generally at Mars, actually. We've been looking at patterns on Mars for a long time. I told you about Schiaparelli, which began in the 1800s. With more sophisticated equipment that we have available now, such as mock imagery, we could see much, much more in detail. And so Mangold performed a survey of mock imagery in 2005 that showed the diversity of pattern ground forms that exist. Here are a number of these forms that range in scales from tens to hundreds of meters in size for these polygons. He performed a survey, a large survey of images, and found that these polygons were also distributed latitudinally. They were only found polewards of around 50 degrees and not found anywhere in the equator. And this is the exact same region where we find the ice. So these polygons have a definite ice-related mechanism for their formation. Later, with HiRISE imagery, we continued using these geomorphological observations to study the pattern ground terrains. And we found, again, with the newer imagery, still the distribution of the polygons is very similar, and the types are very similar as well, but we can see much more in detail. And then again, we use different geomorphological characteristics to find these polygons and describe them, but we find relatively similar things. There's larger polygons further south or further towards the equator, and there are smaller polygons further poleward. But I was not very happy with this geomorphological characteristic decisions and categories that were used. I wanted to use something much more objective. And so what I did is I developed a method to use Fourier analysis on images of pattern ground terrains to determine a characteristic spatial scale representative of that terrain. And then I could easily feed images to this algorithm and plot their distributions of these values across the Mars surface. This would give me an objective way of characterizing these same terrains, potentially in a much faster method and without a lot of the subjective biases that are currently present. And so what I do here is I show that I can take a picture of pattern ground terrains. Here you can see these very crisp polygons outlined by these different troughs. And I can filter out a lot of the brightness details and some of the shadows and really focus on the outlines of the polygons themselves. I can capture their edges. And then I can use some of the features of the Fourier analysis to determine the scale most critical for these filters, which are indicative of the size of the polygons themselves. And so essentially what I'm doing is I take a picture and break it up into different frequency components. So we could imagine having, instead of a picture, we have a line, and this line has different frequency components. So the line itself might look like two sine waves added up to each other, but when I look at its power spectrum, I can see that there are two specific frequencies that correspond to this, and that if I add up waves with these frequencies, I can instead recreate this line. And that's what I'm attempting to do with the images as well. That looks instead something more similar to this, where here I have, again, two different waves, one in the horizontal direction and one in the vertical direction. And these waves have different amplitudes as well and different wavelengths. And so when I take the 2D power spectrum of this new picture, using very similar means from before, I can focus on the regions where I have the most power, the most importance of waves with those characteristics. And so again, I find waves in the horizontal direction and in the vertical direction of various wavelengths as well, corresponding to their actual wavelengths in this picture. And so what I do is that I first look at actual images of pattern ground and find a 1760 by 1760 pixel subset of each HiRISE image. And I used the exact same as those images used in the previous survey from Kreslowski and Korten and Niami, which I showed a few slides ago. I take this 1760 by 1760 pixel subset. That way, I can rotate all of the images so that they all have the illumination directly from the right. And then I can take different sized subsets of this larger image. I take two of them specifically, a 512 by 512 pixel subset from the center and another 1024 by 1024 subset. This allows me to see if I have different results from the different sized images. Then I use my 2D Fourier code to find the power spectrum at a given vector of spatial frequency with Cartesian components kx, ky. And then I focus on only the frequencies that correspond to resolvable objects and are in the positive x direction, because I have symmetry due to the nature of the image. And then finally, for each image, I find the characteristic spatial scale lambda, which I call the characteristic spatial scale. And that is the sum of the power spectrum in both the x and y directions divided by the sum times the x frequency. And so, for example, I could take this image, and when I break it into its frequency components, I can look at its discrete Fourier spectra here. So one thing is that it always looks like a butterfly shape in these images. I only look at one of the so-called wings because I have symmetry on both sides. I also then limit my the area that I look at to just that's actually resolvable in the image to the actual eye as well. So I can ignore pixelated variations and some of the large scale variations as well. And then I sum all of these and I divide them by the sum times their frequency, and that gives me this power weighted spatial scale. And so if I look at it, at the distribution of values for those images from the previous subsets, I find something very interesting. And first of all, that's that at about 60 degrees, I have a sharp transition from the types of polygons I have. North of 60 degrees in latitude, I have only short or small scale polygons. And south of 60 degrees, I have a much greater diversity in the sizes of the polygons, or at least the characteristic spatial scales of the polygons that I find. I still find these smaller values, but I find much, much more larger polygons as well. And this is the same sort of thing that was found in all of the geomorphic sub-surveys that were done, all by subjective eye cases. And so if we look at this on a map, we can see again that all of the northern polygons are very small, between 4 and 7 or so meters in characteristic spatial scale. And to the south of that, we have a much greater diversity of polygon sizes. And there is some possible geographic coincidence of a number of these as well, where we have much, much higher characteristic spatial scales in this specific area versus, say, over here. And we don't necessarily have an explanation for that quite yet. One thing that I did find, though, was that by looking at the 512 pixel images and the 1024 pixel images, I was able to pick out something very, very interesting. You would expect if this characteristic spatial scale that I'd chosen was a good tool to use, that no matter what size image that I used, I should find the same characteristic spatial scale. And that is true for most of my images. Here, the black show essentially a one-to-one relationship between these two different image scales. And the red show essentially the same thing, but at larger values as well. These blue ones, though, turn out to be a different type of polygon than I had expected to see. These blue ones show that I was missing out on some of the important parts of the power spectrum at larger polygon sizes. And so when I looked at what these images looked like, I saw something along these lines. And these are what I like to call multi-scale polygons, where we have multiple scales of polygons present simultaneously. We have these much, much larger polygons with these large troughs that outline them. And then we have the smaller polygons that we can find within a single given polygon. And we find this case all over. There are many, many places where we find these multi-polygonal scales. And so it might be useful to use the multi-sized images or to pick your image size such that you can best find the scale that you're aiming for. But that's only true or only important when we have multiple scales present. If there's just one, we seem to pick that up very well. One other problem that is important, though, is that the images that we have to use must still be picked out by eye to avoid the influence of boulders, especially at large polygon sizes. If there are boulders present in an image with large polygons, the boulder's characteristic size will influence the spatial scale that we find. And so this really will affect our image surveys. We can't just automate our image surveys necessarily. We still have to pick out our images by hand. However, at smaller polygon sizes, we don't really see any influence from boulders. So automated searches should work more efficiently at these smaller polygon sizes, which we find most often at higher latitudes. And so what we find is that here we have a characterization of pattern ground terrains, and it yields results similar to geomorphological surveys, but does so in an objective way. The presence of ice seems to be more important than the temperature fluctuation in polygon development. And this is because we still see small polygons everywhere at all latitudes. And so maybe just having ice means that we can make polygons, and we're not really certain that the temperature fluctuation or the scale of the temperature fluctuation is as important. We cannot, however, distinguish between different morphologies of similar scale, which is a benefit that current subjective studies are able to do. One thing we can do, though, is distinguish locations where multiple polygon scales exist. And finally, we have to be careful about choosing our images specifically for large polygons. That way we can avoid the influence of boulders. And so that was one part, and I think now we'll head over and start looking more specifically at the boulders on these terrains themselves. So the boulder is the smallest scale resolvable unit of rock on the Mars surface. They're plentiful on the Mars surface, and we know that they can be hazardous to landers and rovers, but they provide potential sampling sites. And so it's important to look at these boulders and characterize what they are doing. Again, here is the image, my favorite image of pattern ground terrain on Mars, with all of the individual boulders. These boulders are about 3 meters in diameter. So this is a large, large rock. This is something that you could go climb on outside if you so desired. So what I did is I wanted to start out by looking at impact crater features because I knew I would find boulders there pretty regularly. So we first found, we focused on craters that were between 0.1 kilometers in diameter and 1 kilometers in diameter to determine how boulders clusters. Again, impact craters are a source of boulders, and we found impact craters in a variety of degradation states, representative of evolution through time. These weren't the pristine bowl-shaped craters that everyone is very familiar with. These were flat circular features that were heavily degraded. And we had to assume that all of these flattened circular features, which had a distribution similar to impact craters, were actually impact craters as well. And around these impact craters, we found that boulders would appear to cluster in different ways, and I will talk about that in a moment. But the most useful thing that we got from looking at the impact craters is that we could use crater retention statistics to constrain the timescale of boulder clustering. So to begin, here we can look at boulders around an equatorial crater. This crater is at about 20 degrees in latitude. You can see it has a pretty sharply defined rim, boulders making up the rim, and the boulders seem to, when we look very closely at the subset, don't really have any specific orientations or preferred locations around the terrain next to them. However, if we look at a polar crater, here we see a flattened circle. I assume that the rim is where this ring of boulders is, but it is so degraded, I have no guarantee that that is the case. And if we look very closely, we can see that the boulders line up in chains where they touch end to end and outline different shapes on the surface. If we look at the distribution of these boulders around both equatorial and polar craters, we can see that they do similar things. Essentially, you have more boulders near the crater rim, and it decreases as you get away from the crater rim. The boulder distributions are relatively symmetric with the occasional ray or filament-like feature to them. And out here for the equatorial crater, since there's much less degradation of craters at equatorial regions, we actually had influence of other impact crater structures and their boulders. And so we can see from this that polar craters, the distribution of boulders around polar craters, should be similar to the distribution of equatorial craters. It's just that when we look at the boulders themselves, we find the polar boulders are clustered and the equatorial ones are not. So how do the boulders cluster? They cluster in two different ways primarily. First, they can cluster in polygon edges. And here are two examples of boulders clustering in polygon edges. Here, the boulders line up to outline different shapes. And in this one, we have little boulders lining up in the cracks that outline the shapes of the polygons themselves, like this boulder, this boulder, this boulder, this boulder, and this boulder, and even this boulder are all outlining this polygon here. And if you look closely, nearly every boulder in this image lies on one of the cracks. And so this tells me that boulders indeed are clustering in the polygon edges. We also find boulders clustering in another way. This is what we like to call rubble piles. Here we have a polygonal terrain, and on this terrain we have a cluster of boulders here, we have a cluster of boulders here, and we have clusters of boulders here. And even in this case, when possible, we see that the boulders are lining up in the cracks, even within the rubble piles. So here the large boulders are definitely in the cracks, the troughs of the polygons. But when you look closely, you can see the boulders lining up in the cracks of the troughs, or in the troughs of the polygons, in the rubble piles as well. So there's these two different types of fundamental boulder clustering. I am going to focus on the first one, the boulders that cluster in polygon edges, and outline them. The types of boulder clustering we find, though, is that we find boulder clusters in the edges of polygons everywhere, both in here the white circles and the black dots, but we only find the rubble piles in the black dots. So we have rubble piles at higher latitudes and not at lower latitudes. And when we look at all of the craters, over 1,200 craters for our survey, we find a distribution that looks like this. Excuse me. The decline in our distribution compared to the isochron is indicative of the erosion or degradation of the impact crater structures that are no longer there. And this tells us that we have a very active surface at small scales. And our results at larger crater sizes match up with previous surveys pretty well. And for this region, for the given area, 3,200 kilometers, and for the craters with diameter of over 100 meters, the Newcomb production function gives the mean cratering rate of 1 crater per 0.2 million years. And at this cratering rate, the youngest crater in my survey should be within 0.08 million years at 90% confidence. Since we found 7 craters that had potentially ambiguous boulder clustering, this places an upper limit on boulder clustering at around 2 million years. And so this is the time scale which we would imagine an entire population of boulders would become clustered. And so how do they cluster? All of the mechanisms, or most of the mechanisms for boulder clustering on Mars were thought to be the same mechanisms as those that are thought to cluster boulders here on Earth. The most common is found to cause boulders to cluster on Earth is most likely gravitational sorting, where simply these large particles are on slopes and they move down the slopes. However, we have polygons that aren't on slopes, and even those cluster boulders at their edges. There seems to be very, very little topography on these polygons, as much as 20 centimeters of relief over 6-meter diameter polygons. These slopes are not enough to just have the boulders slide down them. There's enough friction that they should stay in place. We could also think of surface creep, which maybe this involves some outside agent, maybe some aeolian processes or sublimation or something else, and that this would drive the boulders into the polygon troughs. However, as far as aeolian processes go, we don't see any ventifacts around these boulders. And we find these boulders everywhere, and we know that there's loose sediments there available as well. So we can't explain the lack of aeolian features, and so we don't believe aeolian processes are likely for clustering these boulders. Sublimation is thought to cluster boulders in a certain fashion here on Earth. I definitely support this idea here by Levy et al. However, on Mars, what happens is that once we've clustered these boulders into the troughs, as shown, you'll invert the topography because the ice in the polygons here no longer have the protection of the boulders. And so this will preferentially sublimate, leaving these boulder tracks, and will invert the topography. And that's the proposed explanation for what makes the rubble piles themselves. We could also have dry cryoturbation as possible. This is likely to form different polygon types in the dry valleys of Antarctica, where we have this perennially frozen ground that is that contracts in the wintertime. Sand grains are able to enter into the cracks themselves, which keep the crack open, and repetitively filling these cracks and opening them and closing them would lead to polygons as well. But this one is not capable of moving giant boulders. We're talking about trying to cluster 3-meter boulders. We can separate pebbles and sand grains using this mechanism, but there's never been seen any boulders to be clustered using this mechanism. Finally, there could be ice lensing and frost heave, and this is a definite possibility on Mars if these polygons are very old. When there might have been a previous warm and wet climate on Mars, which would have allowed frost heave in the near surface. However, it's been very cold on the surface of Mars for many ages, the past millions of years, and so we do not expect the surface to be above the freezing point of water on a seasonal time scale. And that's what's necessary to melt the polygons enough and then refreeze them to form these large ice lenses that are capable of moving large boulders. I propose a new mechanism, though, that depends on the Mars environment itself. So what I show here is that in this first step, I picture boulders sitting on a polygonal surface represented by these different cracks in the surface, and that the boulders are sitting at different distances away from these cracks. This allows us to outline a number of different features of this idea. In the wintertime on Mars, carbon dioxide frost freezes out onto the surface and forms a layer anywhere between centimeters to almost a meter in thickness. I propose that this thick layer of CO2 frost is capable of locking the boulders into place as long as they're within a certain size. So as the frost solidifies, it keeps the temperature of the surface at 155 degrees Kelvin, the sublimation or condensation point of carbon dioxide frost. While the surface is locked at that temperature, though, the subsurface will continue to cool. And as it cools, the ice there will contract. When it contracts, we form the cracks again, and the boulders move relative to their earlier positions because they are locked in the ice with the ground underneath them moving. And so when spring comes and the frost sublimates away, the boulders are lightly placed back on the surface, and they do so in new positions. So this boulder, which was in a crack, never moves. This boulder, which was in the middle, would be stuck in the middle since all of the contraction and expansion happens from that point. But near the cracks, when we expand, we reach new locations. So this boulder would have fallen into the new trough and have a new location. This boulder I show here is too big to be trapped in the ice. It crushes the ice, and so it stays in place. This is a prediction that I hope to test. And these two boulders both move closer towards their polygonal edges. And so for those of you that are better visual learners or auditory learners, I also have this written here in a short form, that thermal contraction and expansion of ice in polygons also moves the boulders. I suggest that the seasonal CO2 frost formed during Martian winter prevents boulder movement inward during the contraction phase. The boulders then move outwards during the expansion phase, and this leads to progressive movement of boulders towards the polygon edges. Yes? The same size of the polygons themselves, so meters. Or on a seasonal basis, I don't have a prediction at this point in the talk, but I'm going to use some models to show what I think the seasonal motion will be. I'll get there. So first, I have reason already to believe that the CO2 frost is strong. Seasonally, we see CO2 frost geysers form in the springtime. And what happens is that the sun shines on the surface. Since the ice is relatively translucent, it's absorbed by the underlying layer, which heats up. It then causes sublimation of the overlying seasonal cap. And as the pressure builds from this increase in vapor, we break through the cap and entrain CO2 dust that forms these geysers like these over here, where we see these dust emanations blown by the wind. And these are about 25 meters or so in length here. And so to entrain that much dust and blow them these distances, the seasonal cap must be able to withstand some significant stresses. And so we first see that, again, vapor generated at the soil frost layer will generate heat flux from below. This vapor travels through the frost and can then refreeze and sinter the frost slab. We know that dust plumes in the spring show that the slab is capable of entraining this vapor and trapping it. We also see that the grain size of the frost increases over time in spectral observations, which is another line of evidence suggesting that the frost slab strengthens over time. And finally, the opacity of frost changes too, also suggesting the same thing. And we have some experimental evidence that the CO2 frost strength should be within 0.1 to 1 megapascal in strength experimentally here in the lab. And so my first order of business is, can the boulders actually get trapped in the CO2 frost itself? So here what I did is developed an order of magnitude model for what the stress in the ice would be induced by the boulder. And so that stress, which is a force per area, is the friction force that the boulder would experience times the area in contact with the ice. This is equal to the frictional coefficient times the density times the gravity times the diameter squared of the boulder divided by the height. And when I do this for various frost slab thicknesses, I produce this graph, which shows here I show the maximum strength of the CO2 frost. And each of these lines corresponds to a different CO2 frost thickness, from 0.1 centimeters to 45 centimeters. And we have as much as a meter of frost in some locations. And what this shows is that if the CO2 frost is as strong as we've ever seen it experimentally, then we can trap 9-meter boulders in this frost. If we only have 45 centimeters thick slab, that's a really big boulder. But if it's at the lower range, we're still talking 3 to 5 meters. And these are the sizes of the boulders that we see clustering nearly everywhere. And so this leads me to believe that it's very reasonable to think that this frost can indeed trap the boulders at the surface. And so the next thing I sought to do was to develop a thermal model of the subsurface. That way I could calculate the stresses and how much contraction the subsurface would experience as well. So what I did is I simulated the temperature with depth and with time using the method of James 1952. In this, I solved the linear diffusive heat conduction equation in a semi-infinite solid with a periodic plane source. And I take surface temperatures from the Mars Climate Database from Forget et al. 1999, and then interpret between the points with the cubic spline. When I do this, I am able to calculate the temperature at depth for any given day in the Mars year. In the upper left here, I show you the calculation I use to do so. And what we see are these different isochrons. And at different times of the year, this time here, Sol 570, and this time here, Sol 30, are two different times during the winter. And this is the period of time where you might expect the contraction of the ground to occur. So the difference between these two isochrons represents the change that occurred while the boulders might have been locked in place. And so I take this information and I feed this to a stress model to calculate the contraction or expansion. So I use this model in ADINA, the Automatic Dynamic Incremental Nonlinear Analysis Program. And in this, I develop a 2.5 meter radius by 4 meter depth rotationally symmetric cylinder, which I model as a single polygon. I take the temperatures from the thermal model I just discussed, and then apply certain physical coefficients that have been used in the literature before. These include Young's modulus, the coefficient of thermal expansion, Poisson's ratio, all of these representative of pure water ice. Soil ice mixtures are not very well understood, and since there's as much as 90% water volume by ice in this location, I feel this is an acceptable assumption. I give this polygon a free surface on its upper and right boundaries, and allowed zero displacement on its bottom boundaries, and then allow ADINA to compute the stress, strain, and displacement using its finite element procedures. And this looks something like this, where here I have the top of the polygon, and this is the center of the polygon. The colors represent the amount of contraction that would have occurred in the polygon relative to a polygon whose entire temperature is at the yearly averaged daily surface temperature. So this polygon experiences approximately 2.5 millimeters of contraction at its uppermost edge, and expansion at depth at this given time. What I do then is I look at two specific times. Here is the case where I have, this is data taken from Kelly et al. 2007, where I plot the frost thickness for this location as a function of solar longitude. And I pick the two times where I have 20 centimeters of frost. I then use the thermal model to calculate what the temperature profiles were with depth at these two times. I subtract them to find the difference and see what the contraction that would have occurred in that period of time. And so here I have those two different times, again, compared to the yearly averaged daily surface temperature. And what we can see is that we have, at the later time, LS 375, we have deeper or brighter pinks that extend to lower levels, and the green also reaches much lower levels, and we have significantly less red here. When we then subtract these two images, we find the difference in radial displacement between those two times. And up here at the top, we do indeed have non-zero displacement. In fact, we find a tenth of a millimeter of displacement per year would be our seasonal average of boulder movement. So this more detailed but still order of magnitude thermal and elastic modeling suggests that we have a tenth of a millimeter of contraction while the boulders are locked in place. This would be the amount of contraction or movement of the boulders we would expect on a seasonal basis. The mechanism should be more effective, however, at higher latitudes because we would have thicker and longer lasting frost cover. The mechanism should also be more effective at higher obliquity due to thicker frost at a given latitude and larger temperature changes at that latitude as well. And finally, with this magnitude of seasonal motion, we would expect a time scale of 10 to the 4th to 10 to the 5th years for boulder clustering to occur. And this is consistent with the findings from crater retention studies. And so this leads us to believe that at the very least, with how much variation we have from potential order of magnitudes in our coefficients that we chose, Since we use pure water ice rather than soil ice mixtures, this extra order of magnitude until we get to the cratering constraints definitely works in our favor. Essentially, we can cluster boulders on very quick timescales, and we can cluster large boulders on these timescales as well. There's a few testable predictions we can make based on this. First, the size threshold for clustering of boulders depends on frost thickness and strength. And so the size threshold for clustered boulders should change with latitude because the frost thickness varies with latitude. And the boulders should move today, although we cannot yet observe changes at this scale. Tenth of a millimeter is not enough to cut it when we're dealing with 25 centimeter per pixel imagery. However, I do hope to continue looking and test some of these predictions. And so my first goal, I have a proposal out looking to look at a number of these images with latitude. We have two possible traverses here where we stay at the same longitude as much as possible and test a lot of variations in the latitude to determine if we do see boulders clustering differently at these different latitudes. Maybe we find size variations, maybe we find something else. But it would be very interesting to see how this works and compare multiple different geographic areas as well if possible. So to conclude, I'd like to again state that boulders cluster, and they do so at polygon margins, meaning they have to move. These boulders have to be moving, and they do so due to the seasonal thermal contraction and expansion of the ground ice, combined, I would say, with the seasonal appearance of the carbon dioxide frost. This drives the boulders towards those polygon margins. We predict boulder movement rates of approximately 1/10 of a millimeter per year and clustering timescales of 10 to the 4 to the 10 to the 5th years. And before I finish, I'd like to acknowledge my funding source, NASA Mars Fundamental Research Project. I'd like to thank my co-authors, Eric Asfog, Mikhail Krasovsky, Yarmo Korteniemi, my PhD institution, University of California, Santa Cruz, and again, my current institution, Pierce College. Thank you very much, and I would like to answer any questions.
Travis, I've just got a question about why the mechanism that you've outlined doesn't work on Earth because water ice is too weak to hold boulders of that size?
No, so water ice is actually stronger than the carbon dioxide ice. The problem is that water ice stays at the freezing point, and we don't have to, we can't trap ourselves at the freezing point necessarily like we can trap ourselves at the carbon dioxide frost point. We can actually get ice at the surface to go down to much lower temperatures. We can have ice at -20, -80 degrees. We can't trap the temperature of the ice, and so we can't really know that ice can be contracting as well with the subsurface, and so you're not really trapping the boulders because the ice will contract just as the subsurface will contract.
Thanks. That was interesting. Can you go back from the boulders to the polygons themselves and compare a little more Earth and Mars? My impression was that Earth's polygons tended to be smaller, and I don't know if the mechanisms are really the same or not.
The polygons on Earth range in scales quite a bit, anywhere from 1 meter to tens of meters. And on Mars, we definitely kind of have the same sorts of scales. We can't really see 1 meter polygons from satellite imagery, but we can definitely see 3 and 4 meter polygons. So this suggests to me that there are probably 1 meter polygons too. And the other polygon scales on Mars can again range up to hundreds of meters. As far as the mechanisms go, there are many types of polygonal ground just in general, but if we focus on permafrost pattern ground specifically, it is essentially just the two that we look at, frost heave and thermal contraction of ground ice. Frost heave is more of a convective cycle that's developed, and thermal contraction is, we can still develop some of these convective cycles, but it's more about producing a wedge in the crack. And
those processes work on both planets.
Those processes should work on both planets. The problem with frost heave on Mars, though, is that it won't work there now because of the temperature situation. But in a warmer climate, it definitely could have. And I believe Zent et al. Has done some obliquity calculations that would suggest as recently as 4 million years ago, you might have been able to have frost heave on Mars. But more recent to that, unlikely.
Hello, over here. Other side. Hi. Those timescales are really interesting because they're really, really short, geologically speaking. So I'm wondering if somebody gave you a lander and you could actually do some low measurements. I know that the Martian atmosphere is really thin, but it does pick up dust particles, and there's sizes of things between dust and boulders, yep. Right? And I was wondering at what scale you might expect the atmospheric movement to overwhelm this kind of thing in terms of rock or pebble or movement.
Well, I don't see the Mars atmosphere really able to lift particles greater than the size of sand grains.
Or even roll them along?
Or not a pebble, definitely, but maybe roll sand grains. But then in this region specifically, we don't see ventifacts, which is kind of the formations that sand grains would form around a boulder. And so this kind of leads me to believe that there's not aeolian processes that are dominant at the very least. Maybe there are aeolian processes, but they are overmatched by the other paraglacial processes that are present there. Yeah, the lack of ventifacts, I think, was I didn't see anywhere except on dunes themselves. But then dunes aren't actually patterned in this fashion. So yeah, I would say it's unlikely that aeolian processes are likely for moving boulder-sized objects. The relief on them is really small. It's possible, but we're talking 10 centimeters of relief over 10 meters of polygon size, possibly. So I just don't see that being it's relatively flat as far as I think the wind is concerned.
It seems to me that some of this could be done in the lab experimentally. Have you done any experiments like that, or do you plan to?
I would like to. I've not had the opportunity to do so much. A lot of the subsurface ice stuff, another group has done a little bit with vapor diffusion of ices into solids, just to see how much ice we can store in the substrate, and if it's likely to be from kind of atmospheric deposition as a layer, or if it's kind of this vapor diffusion that's produced the ice. And Phoenix showed that we have kind of this larger crystalled ice, so it's more likely to be not from vapor diffusion. But then to get the movement of things, I feel like will be difficult, because I mean you need to trap this. We don't know how the ice is really distributed over time on Mars necessarily. We know how its thickness changes, and we know how the grain size changes, but we don't know how it's if it's snow really, or how this layer forms, and how it dissolves. Does it dissolve from top down or bottom up, and how? So there's a lot of complications with the CO2 frost slab in the lab and trying to trap boulders within it. I've tried to come up with a few experiments, but everything's got holes in it, essentially.
Yeah. I believe you said that you only find these boulders in impact craters. Is that correct?
We find boulders all over the place, and we don't find craters all over the place, necessarily. But this terrain itself has evidence that it erases impact crater structures. So just because we see boulders and no crater doesn't mean that it wasn't from a crater, necessarily. It's my opinion, and just an opinion, that most of the boulders on the surface are from impact events, whether we can see them or not.
Well, that kind of brings up, on the big volcanoes, are there any impact craters way up high that have the same polygonal structure that you see at the high latitudes?
Not really.
Okay.
No. Any other
Last two
questions?
questions.
Oh, okay.
I was going to say, as I understood your model, you would expect a certain number of the polygons to have boulders in the center. And
Yes, if we had absolutely perfect polygons, I would expect them to be in the very center. But I think most polygons have kind of irregular shapes, and that kind of, there is no true center to a lot of the polygons.
I was holding that thought throughout your talk, and then you put up that very last slide, and it may just be wishful thinking, but I thought I saw some boulders in the middle of polygons.
Quite possibly. Sometimes my eye wants to see those, see that stuff too. But yeah,
South Central.
I think this one here possibly. Yep.
I wonder if you could describe the right after an impact, what the distribution of of boulders would be. Are they just over the crater edge?
Well, there's some inside of the crater itself, as well from collapsing of the edge into the interior. But then for the most part, the boulders, they have the highest number of boulders and the largest sizes closer to the crater rim. And then it decreases, the number of boulders decreases with distance from the impact crater. They're relatively symmetric, kind of however you want to slice it, but there are occasionally some more almost like flame-like or filament-like structures to them. So something that might be indicative of not coming in at a high angle, or maybe having kind of heterogeneities in the subsurface. Maybe you have different layers and that cause things to blow out differently, or maybe there was already a fault somewhere and so a line of weakness. But for the most part, all the craters are very, very circular. They're either degraded or pristine, and the crater rim is the most identifiable thing simply because the boulders are present, and then yeah, it decreases with distance.
Okay, Travis, we have a special SETI mug here for you, a little bit smaller than the boulders that you're able to resolve with HiRISE, but hopefully it'll bring you some caffeinated nourishment in the coming months.
Thank you, and thank you all.
Please join me in thanking Travis. Thanks.